Islam Khan, welcome to the podcast.
Yeah, it's great to be here, and I'm very excited to talk about science, cosmology, and physics.
Yes, so you're the first cosmologist I have on the show. I have had a different scientist who studies the origins of life, Ben Pierce, and so we've talked about space a little bit already on this show, but not about what you refer to as early universe cosmology. So first things first, why don't you tell me, what does a cosmologist do?
Okay, so cosmology, it's the science of the universe. So it's telling you things about how the universe formed, the origins of the universe, how it evolved over time, and how it ended up to the state that it is now. So it has a lot of, you know, unknown things currently because 95% of the universe we still have no clue about. So cosmology is just answering questions that we are nowhere close to, in my opinion.
Okay. Yeah, and so what's fun, for my viewers is that, Islam and I are actually doing this on video so we can see each other, and what I absolutely adore so far is that Islam has a huge smile on his face, which to me indicates that this is a guy who's super passionate about this topic, and so, I'm curious real quickly here, if you can tell me, how the heck did you get into studying this topic in the first place?
So my story is so I've been curious about these topics for as long as I can remember. So when I was younger, I used to spend all my time watching documentaries on space exploration, documentaries on the cosmos, like dark energy, dark matter, where all this comes from. So the unknowns of the universe always fascinated me a lot, and seeing the vast number of things that we have no idea about, and the big questions like what's the origin of the universe, and so before coming to what's the origin of life, you have to think about where the origin of the universe is, and those could be connected. So there are philosophical ideas that connects life and the universe, like that life, the universe only formed, and it's the way it is now because there's a conscious who can study it. So there are theories like that. So I'll talk about that later. Um, so I really got into these topics on cosmology in this field when I was in A level. So in my country, we don't have high school. We have O levels and A levels. We follow Cambridge. So
When you say your country, you mean
in
Bangladesh?
Bangladesh, yeah. So
Yes.
Bangladesh, we follow the curriculum of British. So we have A levels. So we had to take classes, courses on astrophysics, particle physics, and all that. And seeing things like we have no clue about the fate of the universe. We don't know, is it going to be expanding and stretching out forever, or is it going to contract? Is it going to keep bouncing? So seeing this, like we have no idea about how the universe is going to evolve in the future. We're not going to be around to see it, but a lot of things could be happening. Or if there's multiple universes, like so seeing all of that is very, very fascinating for me. I'm like we can't actually do research on the unknowns of the universe, like multiverse and all that right away, but we can start somewhere. So I that's what I did. So I came to US to do my undergrad because our country we don't really have good physics programs. So that was always the plan: pursue physics, get an undergrad, get a bachelor's degree, get a PhD, postdoc, and then see what happens. But it's going to be exploring science.
That's really cool. I have to ask this question because you used a few words right now when you were talking, like bouncing and stretching. To me, that seems so kind of abstract, and I don't understand. Is the universe kind of like a ball, or is it kind of like an elastic?
So there, you have to look at it two different. You have to look at it differently. First is the universe. The way the model is infinite. So there is no way to picture the universe because it's infinite or it's so large that we cannot never see the end, or maybe doesn't have an edge. The other way is observable universe. So if we're from where we are, from our perspective, we look at every direction. we can see until a certain point, because light travels at a limited speed. So it can travel 13.7 billion light years. So that's about, I think, 46 billion light years in diameter or radius. So our observable universe is a ball because we can look that far and every direction. But the actual universe, the model is infinite, and it could have multiple bubbles of universes. So those are things that I'll get into later. So the
Okay, so
multiverse,
that's what you mean by multiverse,
yeah, no,
essentially.
so multiverse has four different levels, and I'll actually have to get deep into that. But the model is it's infinite in every direction. So regardless of if you're like looking at the universe from outside the universe, if you could do that, then it would just be an infinite space, and lots of things could happen in between that, depending on what the theories are predicting, but still infinite.
Okay, so for people like myself who are know nothing about space other than how pretty the stars are, um, so something like we know that Earth is in the Milky Way galaxy,
Mhm.
and then the Milky Way galaxy is inside of what?
So the Milky Way galaxy. So if you increase the scale, so we
Hmm.
are part of a local group. So it's like if you go to higher and higher scale, you end up seeing a cosmic web. So it looks like a web because um, that's what it looks like. So when you see a web and you compare the simulation, we can actually see that far. We can see some of it, but it looks like a structure of a web because most of the galaxies in the stars are within those dense regions. So you go to higher and higher scale, you have multiple galaxies together, bounded together, and then you have the local group, and you go higher. So these have different names. I don't remember all the names off the top of my head, but larger scale, you end up seeing this web kind of structure, and we are in one of those dense regions.
Yeah, and I mean, it's really just the reason I brought it up is really to just give the scale of what a universe is, right? I mean, it's just like you said, the observable universe includes us in it. It includes Jupiter. It includes the Milky Way galaxy, right? It includes all of these various galaxies within it. Correct?
So these galaxies are very, very close to us. The observable universe goes way back. It's much, much larger. So it's hard to explain what 46 billion light years is. So light taking can travel. We can see the distance is 46 billion light years, but you can think of it as light traveling for about 14 billion years. So light traveling for 14 billion years, that's how far it goes. That's the size of the observable universe.
Whoa.
It's that large.
That's that's crazy. It's crazy that it is so big out there.
Yeah, so the interesting thing is this appears large to us, but this is a very, very tiny part of the entire universe. That's what makes cosmology so fascinating, is because the part we can see, space looks vast. But if you look at the model, the theories, it's predicting that there are infinite number of observable universe. So what we can see, there are infinite number of this observable universe depending on where you are. So we are looking at a very, very small portion, a very tiny portion actually.
Wow. I mean, really. And I know we're not specifically speaking about life in other places, but I have to ask you just out of curiosity as a human being and with the knowledge that you have, do you think we're alone?
Not likely. And it goes back to what I said previously. It's because the universe is so vast. Um, so our observable universe is large enough to have multiple life forms, even though we haven't seen one. But you know, Perseverance just landed on Mars, so let's see what happens. Um,
Yeah.
but if you look at the entire universe, even though we are not in contact with them, even though they're beyond our horizon, there's a very, very high chance there's life multiple life forms out there.
Do you think that science will find them before you die?
Um, I'm hopeful that at least we'll be able to find microbes, and it's a very active field right now. So currently, there's a lot of push on finding life out there. Recently, there was observation on there was a prediction or like observation and speculation like there could be life on the clouds of Venus, but it turned out that's not the case. But people are still pushing for it and looking probably beyond solar system, not right away, but in the future. But within next 40, 50 years, I think we'll find something.
Yeah, I really think so too. I mean, we could who knows, we might find a microbe in the Martian soil that we bring back, right? I mean, that's a very real possibility.
Yeah, 2026, that's when it's coming back. Uh, so we gotta wait and keep our fingers crossed, I guess.
Exactly. So let's get into it because I know that you're super excited to speak about multiverse theory. I have no idea what it is. Give me the general lowdown. What is a multiverse?
Okay, so I need to start from the bottom. So this is something I actually work on. So I work on the inflation theory. So the inflation theory is telling you that the universe underwent a very rapid stretching, a period of very rapid stretching. So I'm saying stretching and not expand because when I say expand, it gives the idea that, oh, maybe the universe was tiny and then it expanded over time. But actually, it was always infinite, a small portion, a very, very tiny portion stretched out over time. Um, if you look at a small portion, yeah, you can say it expands, but then it gives you the idea that the universe is finite, but it's actually infinite. Infinite. So,
I'm going to interrupt you right here, just for a second here, just to ask you a question about that point. Um, how does if the universe is so large, how does science know that it has stretched?
yeah, so I'm so that's the interesting thing. So we have many observations from before, and inflation actually solves them. So, for example, if you look at one direction and you measure like one patch of the sky and you measure the temperature, and then you look at another direction and you measure the temperature, and let's say the temperatures are the same. It's about, let's say, 3 kelvins, very close to zero. So the question is, how can this point, this patch of the sky, have the same temperature as that patch of the sky, even though they have never been in connection? They were never in contact. So that was a question, and no one knew how to solve that. And another thing was why the universe is so flat. So imagine you are sitting on a painting, and it's all scribbles of different colors, and you can see the scribbles. Um, but let's say the painting stretched out very rapidly, very, very large. Then you would only see one color. You would not see the scribbles anymore. It's gonna look, you'll just see one color, and you would never know that there were scribbles before. So our universe appears to be flat. It means something happened which smoothened it out. So there are more questions like I'm not gonna get into that. Like, there could be monopoles, the predictions of monopoles. That's a different thing. But the thing is, we can observe two different points and see that there's no way they have the same temperatures if they're never connected. So inflation answers or solves these problems because if inflation did take place, it would explain why our universe is so flat, why it smoothened out, and how can different parts of the universe have the same temperature. So these observations gave clues that the universe stretched out so rapidly. And when I say stretched out rapidly, you have to think about the scale of the stretching. So a size which was much much smaller than the size of the proton expanded to the observable universe. So it's much smaller than a proton. Imagine that tiny bit. expanding to the observable universe. That's how much it's expanded. And that's how flat the universe is. So seeing those observations, the inflation was first developed by Alan Guth in 1981. Actually, 79. He had it down on his notes. And that's how it solves the problems. And we know that it stretched out so much. And if it did stretch out so much, that means the universe must be very, very large. And it goes way beyond what we can see.
Wow. Okay, so that's inflation. Now, what I hear from multiverse is several universes.
Yes, so multiverse is a consequence of inflation. So,
Oh,
so because inflation had to take place to solve these problems, then it has these consequences, which is you would have multiverses. So let me go over what multiverse is. I know there are movies and a lot of different movies use parallel universe and all these theories, but it kind of changed what it actually is. So we should not even use the word parallel universe. It's all multiverse. So let me talk about level one multiverse. So Max Tegmark, he defined what each of these are because you have four different levels of multiverse. The first one is simple. It's just saying that our observable universe is finite. We cannot look beyond it. So there could be another universe which is far away from ours. We're not in causal contact. So when it's a causal contact, it means light from our universe is never going to reach the other universe. So we are getting separated over time. So there is no way we can ever contact them. So that is a multiverse. It's so far away from us that we cannot contact them. We don't know what's happening there, but it's likely that it's very similar to ours. The temperature, the galaxies, how it ends, planets forming. So that's level one multiverse. It's just saying it's finite distant away, but we can never connect them. So that's why it's a multiverse. So what inflation is saying is that so it comes from quantum mechanics. So inflation, so I'll get into quantum mechanics probably later. So inflaton field. So inflation is caused by a field, a quantum field. So a quantum field is how we define particles in particle physics. So there's no such thing as a particle, but fields. And once you put enough energy, they get excited, and that's why we see particles. You may have heard about the Higgs boson, the Higgs boson, the God particle. So it's actually the Higgs field that's always there. If you pump enough energy, then you can see the Higgs boson. So the inflaton field is a quantum field which has this property that it spreads out. So it's a quantum. Quantum mechanics has many different weird properties. One of them. So I know I'm getting into
it's
complex
okay. Keep going.
ideas. So the thing is that the inflaton field can it spreads out. It has a property, and because of this, it affects different regions of the universe differently. So it in our universe, inflation happened and it stopped. But in a different region, maybe inflation is still taking place. Maybe another region, the inflation was much shorter or longer. So depending on how it affected each region, you have different bubbles, or you could think of the level one multiverses embedded into bubble universes. So you know how you see in animations that you have blank space and you have bubbles of universes. That's what it's referring to. That's level two multiverse, because not only are they very far apart, we can never be in contact with them, and we can't even detect them because we can't even see beyond our observable universe. But think about other bubble universes which are way beyond. So that's level two multiverse, and it gets more and more complex as you go to level three. So level three multiverse is coming from it's called many worlds interpretation. Um, or many worlds theory. So this is very popular in popular science because it talks about doppelgangers and explaining things like, oh, the only reason you're doing this, you made this decision, is because in the other alternate universes, it made the other choices. So it's popular, but if you want to understand what the many worlds interpretation is, it's just saying that, to give a simple example, if I roll a dice, it has six sides. So if I roll a dice and I get a six, that means right when I rolled it, all the universe just split into six different universes, and in each different universe, you had each number. You had 1 to 6. So what it's saying is, every time anyone makes a decision, or any time anything happens, the universe splits up, and the other things, the alternative things happen in the other universes. So the question is, when you say split up, do you have copies of yourself or not? So that so we don't really have an answer to that. There are different ways to explain it. Maybe it's all abstract, or maybe it's physical. Maybe it does split up, but the key idea is every alternate things happen at once. So whatever happening now, so I'm talking to you right now. Let's say I decide to, um, stop the recording or something. So in another, so that immediately um, it would split up. It would be different universe, and in the other universe, I did the other thing, which I continue talking. So every time anyone makes any decision, you have multiple copies of the universe. So that's very complex. That's the idea of level three multiverse. And Max Tegmark can explain this way better than I can. So that's level three. Level four is very abstract. Level four is telling you that maybe very, very far away, the universes don't even have the same physics laws that we have. So maybe the laws are different, so everything looks different. Um, Maybe what we see as a circular motion, maybe it's the motion is has a different shape or something. So level four, it's kind of abstract. We can stop at level three because four, none of us understand it because we only understand the physics laws in our universe, but it could be very different in the other universes. So yeah, so that's level one to four in summary. And Max Tegmark has a podcast episode. So Sean Carroll has a podcast, Mindscape, and they talk about this for a long time, and they go into great details on the different levels of multiverse.
I didn't know that multiverse was what people were referring to in pop culture as parallel universes. So that was very helpful for me to understand that when you said, "Oh yeah, in pop culture it's called this," I was like, "Oh, okay." Um, so now I have a bazillion questions, of course. The first one being on I'm kind of fixated on this third many worlds theory because it's something I've always kind of said, yeah, right. You know, like, come on. There's no way there's like physical copies of each other on different universes and all that stuff. But I mean, is it really a possibility that there could be?
So right now, we can prove that it's not true, but we can't prove that it's true either because these are all based on theories, and it's called interpretation. So this is one interpretation of our reality. So it's telling you, um, so you may have heard of the Schrodinger's cat. So this is what the theory was before the many worlds interpretation, saying that. So I'm going to use a scientific term. It's called wave function collapsing. So it's like when the cat is in the box, it's both dead and alive at the same time. But once you open the box, then the wave function collapses, means it just lands on one of them, one of the possibilities. This is what the previous um, explanation was. But the person, Edwin Schrödinger, he wasn't happy with this. It was like, we cannot observe and change, the outcome. That sounds absurd. So that's where the many worlds interpretation came from. This is more satisfactory, and it's not actually. Oh, it is Schrödinger, but I think it was Hugh Everett. He's the one who wrote it down in mathematical forms. while he was a PhD student at Princeton. So he came up with this theory, even though it didn't get a lot of attention then. Like this explanation is way more satisfying than saying you observe something and you affect the outcome. The many worlds interpretation is saying you observe something, you have you are saying something, but at the same time there are multiple splits and copies of yourself. But there's no way we can prove it or disprove it. It's just fun things to think about. Maybe in the future, who knows? But nowhere we have more important questions in cosmology to answer before getting there.
It makes for good movies at least, right? I mean, really, this is all stuff that it makes for really great science fiction, great storytelling. What about I mean, I've heard some talk about the potential that maybe we're living in a simulation, right? I mean, you hear some people say, "Oh, this is all just AI. We've actually previously existed. We've built all this kind of existence." What about that
Those
possibility? Let's say.
are speculations, and I'm not going to go into those because they're not really predictions of um, cosmology or particle physics or quantum mechanics the way we understand it. As actually, no one understands quantum mechanics. You just get used to it. Because if you think you understand quantum mechanics, then that means you don't actually get it because it doesn't make sense. So the simulations and all that, those are speculations, and I don't really understand where they come from. But based on quantum mechanics that we understand and cosmology and all this, uh, those are kind of different because multiverse is the implication of inflation, and that seems to be more plausible than any of those other theories about holographic universe and all that.
Right. I mean, it's worth asking, right? Ask the scientist, and you'll find out the answers if you can. Um, one thing that I'm really curious about? You said, "Oh, well, this stretching was caused by inflation." What actually do we know what caused the inflation?
We have a pretty good idea of what may have caused it. There are multiple theories, obviously, but the most popular one is telling you that. So it's actually pretty easy to model it. You can think of a ball and a hill, and the ball is slowly rolling down the hill. So you can actually like even picture it. Like you have a ball and it's slowly rolling. And when it's rolling, then it has to satisfy certain conditions. And when it does, so the only way to show it that it affects the expansion of the universe is by mathematically. But if you like to picture it, excuse me, a ball rolling down a hill. So it's not actually a ball; it's an inflaton field. It's a quantum field, and the potential is also coming from particle physics. We don't know where it came from, um, but that's the most popular idea. If the ball rolled down, it caused the inflation. And so the thing with inflation is as it expands the universe or stretches out the universe so rapidly, everything cools down. And but we know that the universe had to heat up again, and because we can see the galaxies forming, we can see the stars forming. So there had to be some way for the universe to reheat. So as the inflaton rolled down, it could have oscillated, and while the oscillation took place, it transferred this energy to back to the universe. So this is called reheating, and this is actually my research topic, understanding how the inflation ended and transferred this energy back to the universe because it had to transfer it back somehow. So the question is, how did it transfer back? There are other theories, of course, but this is the most natural way for the inflaton field to reheat because we know the universe had to get reheated somehow.
Well, so your particular research or the research that you're interested in the most, which of these levels are you mostly working on out of the four that you just
Oh,
told me?
so I'm not really no one. I don't think anyone is working on multiverse theory. Uh,
Okay,
it's a
let's eliminate that one.
Yeah, so these are speculations, things to think about. But you can also as in you can do mathematical formulation on this, but I don't know of anyone who's actually actively working on this. I know Alan Guth has papers on this. Like he has been writing papers on the person who came up with inflation. He has been talking a lot about multiverse theories and all this. But my research is much more physical, not the abstract things. Is assuming inflation did happen, how did the inflaton decay and reheat the universe, and um, finding a way to unify inflation theory and dark energy, because that's the other thing I'm very interested in, explaining what dark energy is, because right now it's still a mystery. We don't know where dark energy came from, even though it contributes to about 70% of the total energy density of the universe. So dark matter, we have no clue. Dark energy, we have no clue. But at least the there could be a way to unify inflation and dark energy. And it's interesting that I bring up the unification, because this is something very it's been around for a long, long time. Unifying theories. Um, this is something most physicists think about. It keeps them up at night. Like, uh, is there a way to unify? So there are four fundamental forces in nature currently, and could it be possible that all four could be unified to form the theory of everything? So three of the forces could be combined to or explained by a single theory called the grand unified theory, or GUT, and then combining all four would give the theory of everything. So what I'm working on is one of those unifications, not the grand unified theory of everything, but at combining or finding a way to explain dark energy coming from inflation, because it looks very plausible that inflation did take place. Uh, so yeah, it's a lot of details there.
Let's take a step back for a second here because you mentioned the theory of everything. The research that you're doing right now, what does that contribute to in the end? What real life kind of practical applications would it have? Would it actually help to discover, how we all came to be? Is that really where you're kind of going with this?
Yeah, so that's always the end goal. Um, and obviously, not one person can do it. It's a collective thing that how a lot of scientists have been doing, and they can achieve if you work collectively. So what I'm trying to do right now is just looking what happens after inflation, because we can observe the universe and we can, um, you know, find out things about inflation, because inflation could have taken place in different ways. The potential, the hill that I was talking about, could have different shapes. So the more we learn about inflation, because that's what I'm trying to do, learning more about what the inflation potential look like, the properties of the inflaton field, the more we learn about that, um, the further back we can go. So if you learn about the inflation potential, maybe it comes from the grand unified theory. So we can trace backwards and find that theory that combined three of the fundamental forces. Um, and then later, theory of everything, that's we are very far from that. But currently, that's the main goal. Like, keep going back to find the grand unified theory, and it doesn't really have any implications on technologies, as it kind of does, because we keep building satellites and we're sending them. NASA is very involved in this research, but it's mainly answering the profound questions, like how the universe began, you know how life formed. So when I say how life formed, I mean how the universe formed, because you need the universe for life to form. So it's answering the profound questions. That's the direction taking my research.
Fantastic.
Mhm.
So then now I have to ask, inflation happened, or we think it happened. Could it happen again, or is this something that just happens once?
So when I say inflation, it's a rapid stretching of the universe. Currently, we enter the second stretching phase. So I mentioned dark energy. So currently, so it was discovered in 1998. that the universe is undergoing a second phase of stretching. So it is happening again. So you're on point about that. And it's not happening because of a inflaton field rolling, but it's happening because of an unknown component, which is dark energy. But we don't know where it came from. We don't know the dark energy could be a property of space itself, or maybe there's an unknown particle we haven't discovered yet. So it could be anything, but it looks like our universe is um, stretching again. So interestingly, dark energy, to explain it, use this term is called the cosmological constant. And Einstein is the one who came up with this term. But when he came up with it, he didn't know the universe is expanding or stretching. He thought the universe is static. And we also knew there are galaxies and stars. So if you have a static universe, which is not moving, the galaxies and all, due to gravity, would cause them to collapse. So Einstein introduced this term in his equations in theory of relativity, the theory of gravity, introduced a term and said you need this term to repel the gravitational forces to keep the universe static, because people thought the universe is just not moving. So when it was found the universe is not actually static but is stretching very rapidly, he took away his term, and he was like, "Oh, that this is my greatest blunder." He didn't. I don't know if he actually said it, but he took away the lambda term. But once it was found out that the universe is going undergoing another phase of inflation, it's not de-inflation, but another phase of inflation. That term was resurrected, and so Einstein, even though he didn't know at the time, his term has been added back to the equation to explain dark energy. So that term that he introduced to provide a repel force to fight against gravity, we introduced that back, and we're saying that that term is probably what dark energy is, even though we don't know what that term came from. That term is could be explaining dark energy and causing this second phase of we call it accelerated expansion, because expansion is not only so space is not only expanding, it's expanding at an accelerated rate. The rate of expansion is increasing and increasing over time.
So this second, let's call it an expansion then. This second expansion, does it have any practical applications to like Earth, for example?
Not really, because
Okay.
if you look at the galaxies nearby, we are closely they're bounded, as in because of gravitational forces. They're always going to be around each other. Well, not always. If you go way past, like in the future, then eventually they'll get separated. But the expansion is happening at a large cosmological scale. If you just look at a tiny portion, and if you have like two galaxies you know are revolving each other, it's not going to affect them. It only affects much larger scale. So if you look at uh, a supernova or a galaxy which is very far away, you can see that it's going away from you because of the stretching of the universe. Not because it's moving away by itself, but because of the stretching of the universe. That's why it's going further and further away.
Okay, I had to ask because I'm sure that we have some listeners going, "Oh my god, the universe is stretching again." And so it's just so people understand, we're kind of like, in the grand scheme of things, kind of like a drop in the ocean compared to the universe, right? I mean, it's you're really a scientist that looks at such greater scale, like the big picture. And everything must be very mathematical, isn't it?
um, Most things are mathematical, that's true, but we still have to picture things, because if everything is so abstract, then it's hard to understand what's going on. Um, but so cosmology is not just like one area. It includes things like particle physics and quantum mechanics. So particle physics is so the field that I'm working on is, you could say, it's particle cosmology, because you have particle physics and cosmology. So it's mathematical, but you have to, change your ideas about what particles are. So when you see an electron, you think, okay, this is a particle. But the way we understand it is it's an infinite field. So it permeates all of space-time, and it's an excitation in the field. So just like the Higgs boson, um, it's a Higgs field that permeates all of space-time, and you have an excitation of that field is the Higgs boson, is a particle, the Higgs particle. So changing our interpretation of everything, changing interpretation of reality. So that's kind of how things are when you work on cosmology and particle physics for a long time. Um, it just changes the way you see things. It is mathematical, but you know whenever you're doing any math, you have to think about, okay, so it's not just happening here; it's happening everywhere in space time, and so the
Does this kind of research cause you sometimes to think philosophically, or to change your thoughts about all sorts of philosophical topics? Like, what's that like on a kind of more, you know, um, yeah, I guess a philosophical level?
Yeah, so there are certain things that do have philosophical answers, and there's intersections. There are, fun things to talk about when I meet someone who's a philosopher. There's cool things to talk about. For example, the lambda term that I talked about, it's the number is very, very, very tiny, and we have absolutely no idea why that number is so tiny. Because if this number was slightly larger, just a teeny bit larger, then the galaxies would have never formed, planets would never formed, and life wouldn't exist. If the number was a little bit smaller, then the universe would collapse and you wouldn't have life either way. So there is a philosophical answer behind this. Why is this number um, fine-tuned, so fine-tuned that allowed all the galaxies and planets to form and eventually life? And the answer, it's saying that what if the universe chose these parameters so that it could form life, so that we could ask the question of why it chose these parameters? So it's called the Anthropic Principle. There are multiple versions of it. This is a simplified version. But the universe is the way it is because there's a conscience to ask why it is the way it is. So these are philosophical. A lot of physicists would probably not like this answer because you can actually
Well, I
test
mean,
it. No.
it plays into religion, it plays into philosophy, it plays into the arts, it plays into science. I think this is the thing that people don't understand about science oftentimes is that you come at it from different approaches, and you have scientists that don't get along. I mean, I'm sure in your field you have people with very strong opinions about different perspectives, don't you?
So in science, if you don't have the evidence, then people don't really value. So yeah,
True.
you can have opinions, but it's all evidence based. If you don't have an evidence behind, so if you say, "Oh, there's multiverses," but I don't have no proof of that, then okay, maybe, but no one's going to actively do research on that because you have to have ways to test it. So the things that I'm working on, we can test it because we have satellites that can make observations. But having opinions on things and not having evidence, usually, in most cases, is not really valued. Even when, like, even if you have been working on a field for a long, long time, you still need evidence to prove it. And that's what, so
Right.
in many talks, when you see people think, new discoveries, they spend most of the time showing why it's true. All the details, the methods they use, all the observations. They won't just say, so I think this is true because that's my opinion. No one's going to say that. So,
Right. But you often, I mean, you see people who have, evidence to support their theories or whatever. But also, like in science, you do have theoretical scientists, right? I mean, people who don't have the evidence, but they really kind of lean towards, like the multiverse, the level 3 theory, the many worlds theory. I'm sure you have some hardcore scientists that really strongly believe that that's what it is.
yeah, so the thing with theorists, so things are changing currently. So right now, more and more theorists are working with experimentalists or observationalists. So if you just have a theory and you don't have anything to prove it, then the theory is just a theory. It if you are an observer, observational cosmologist, and you observe things and you can make sense of the data, it's pointless. So more and more theories are working with experimentalists and observationalists because this way you can make the connections. So currently you will see like cosmology is a field of collaborations. You don't have a person working on just theory. You would always have big large collaborations where observationalists are working with theorists, and that's how you can make the connections, because no one wants their theory to be a theory forever. They want to test
Right.
it and modify the theory, just like inflation. The more we test it, so every few years, the more time goes, the more data we have, the more we know about the inflation field, inflation field and the potential. So we keep observing and then changing our theory to get it to more accurate. So that's been ongoing because we're all working together.
Okay. So we have about I don't know, almost 15 minutes left. I'm curious to know what are some I don't know, maybe advances in research or potential advances in research that you're most excited about.
Well, I'm into space exploration, just like a lot of people, and I'm following Elon Musk's the SN tests, and well, seeing what could happen going to Mars, because our civilization is a matter of time. We're going to take over the solar system. We're going to be multiplanetary species, but we don't know when it's going to happen. So Elon Musk is here, so it's expediting everything. So I'm very excited about this. Like in my lifetime, we probably first humans would you know step on Mars. So I'm excited about that. Um, so right now, advances. Let me think. Yeah, I think it's mainly coming from the astrobiology, finding life, because nothing that exciting has happened other than gravitational waves. So recently, I do discovered that we can see gravitational waves from black holes mergers. So this was a big, big leap. So I got to see gravitational waves. I didn't get into that, but this is a huge leap because we can finally kind of directly observe, black holes colliding, neutron stars colliding, and also the Higgs boson. So this has been around since 1960s. This was a prediction. It was a theory in 1960s that there could be a particle called or a field called the Higgs field, and 2012 is finally when we discovered it in our particle like Higgs in the Large Hadron Collider in Geneva. So these are huge, huge leaps. Maybe it's not going to be, that exciting for everyone, but this is a huge accomplishment in particle physics. We added a new particle in the standard model. So the standard model is not complete. We know that, but adding a new particle that explains so much. It also has its problems, but it also explains many, many things about our universe and of particle physics. So um, gravitational waves, astrobiology, and Higgs particle. Not necessarily in that order, but all three are very exciting for me.
Very cool. Um, before we go, one of the things I really like to do when I have a scientist on the show is get to know them as a person more.
Mhm.
So I'm really curious to know outside of schooling, outside of research, outside of geeking out about space, what are you into?
So I love soccer. We call it football, but in the US it's soccer. And I've been into soccer for a long, long time. I've been following. So I usually watch Spanish League, English Premier League, and Champions League, all that. And we also play soccer here all the time. So that's I'm really passionate about that. And
Who's your team? First of all, tell me
oh, it's
who
Real
your team is.
Madrid, definitely.
Okay, okay, go on.
um, and other than that, I play the classical guitar. So I've been playing guitar for a while, and we have a small band here, uh, all grad students. So we usually perform. So it's soothing to practice when I'm, swamped with work, just leave everything, play classical guitar. So that's the other thing. And obviously traveling, because I'm in Washington, and the best thing about Washington is all the national parks that are nearby. We have Mount Rainier nearby. Vancouver is in diving distance. We have Wyoming, Montana. So we have Yellowstone, far away, but still driving distance. So that's one of the nice things about here, getting to travel, and just the drive is the best part, and also
Yeah.
camping and hiking.
That's really neat. The classical guitar is a surprise. I had no idea. So do you what kind of music do you usually play? Is it really classical music or like do you guys compose stuff?
No, we don't really compose. We cover things. So classical guitar is a Spanish guitar. So I do like the Spanish style of playing. So Spanish finger style guitar playing. It's
So you have the long nails?
um, sometimes,
Okay.
sometimes, but there's strumming patterns that are pretty different from when you have the acoustic guitar. Well, I play acoustic too, and I used to play electric guitar. Uh, but this kind of has a different feel, finger style, plucking style, like different plucking styles. But when you have a band, then we can actually have Spanish because we're all from Bangladesh, or one of our band members was from Kolkata, from India. So the songs we would practice is all popular songs in our country, in our language. So that's what we'd mostly play, popular songs, because
Okay.
usually we have events where you perform. So that's why we need to stick to the songs we know. And in my spare time, I do learn Spanish style, finger style stuff.
Do you guys have a like a YouTube channel or anything?
No, it's a short-lived ban. It keeps changing because every year we have new grad students and then they leave. So we don't really have all that. It's just, you
It's
know,
just for fun.
it's fun hobby. It's a nice way to spend time over weekends.
Yeah, it is. It's again. I'm very curious sometimes because a lot of scientists have very artistic hobbies. They tend to have like whether they paint or they draw or in your case they play music. So I think it's there's some I swear to God there's a link between the arts and science, and I think it has something to do with the exploration and the creativity that you guys all have in common. So yeah, I don't know. I just do you have any thoughts on,
Yeah,
the link between artists and
yeah, I haven't thought about that, but it's true. I've made that observation. Like a lot of scientists, they have hobbies. I know, like physicists, mathematicians, they love playing chess. They like things where you have to think. But in my case, I think most scientists, other than whatever creative hobbies they have, most of us like intellectual conversations, like talking about things, especially with people in different fields. Like, yeah, I hang out with physicists all the time, but if I meet a philosopher or biologist or evolutionary biologist, then you can talk about so many different things that you have never you know about. So
Mm.
that's, I think, something a lot of other scientists share, conversing with people who are in a different field and learning about the different aspects. I think that's something very common with among scientists.
And that's really curious because artists do that as well. So a lot of, like, performing artists will, have, great conversations with film directors, or they'll have great conversations with a painter will have a great conversation with a cello player, like, so you have this kind of weird camaraderie that happens within the scope of their respective industries. Um On that note, now I'm really curious to know if you could have a conversation with three different people in three different fields. What topics or what fields would you choose?
Well, anything really, because the things that I enjoy learning about is history and evolutionary biology as well. So I like to learn about how civilizations evolve over time, and that's some things I do watch, read about history and history channels. Evolution is something I'm very curious about because we keep finding new things about how humans evolve over time. What else? well, these are my interests. I don't know if you can make connections, but it's always, conversing and learning about those fields, because civilization and evolutionary biology, those are two things. Archaeology sometimes. Um, yeah, I think in terms of science, but I do know a lot of astronomers and space explorations. So those are connected, very connected. Astrophysics, astronomy, cosmology, particle physics
Of
connected.
course.
But beyond that, I would say, yeah. So civilizations and so history and so Richard Dawkins, like I follow his talks, and he's an evolutionary biologist. Um, yeah, so that's something I'm curious about. And there are also talks like Neil deGrasse Tyson and Richard Dawkins. Those are very interesting because you see two totally different fields, and they're talking about things, even though they don't understand that it's not their field of expertise, but they can still they know the scientific way of how things work. So it's interesting, even though different fields, you still have the same way you have evidence, and that's how you come up with conclusions. That's not changing, even regardless of which field you're working on.
True, and they're very good at explaining things for the public. We have about 2 minutes left, so very quickly, what is your dream job?
Dream job. I just want to be able to continue doing research. So it doesn't really matter whether I'm a faculty at a university or doing full-time research at a lab. Let's say I'm working in NASA or work at CERN, wherever it is, if I am able to continue doing research and learning new and new things, that's all that matters. It's not like, oh, I need to work at this particular place. It's just having the opportunity to do research. And because it's all collaborative, now I can work with people who are in different parts of the world. And now, because of the pandemic, we can do it more now because it's all online. So keeping up with what's happening around the world with other researchers and working with them, that's the dream. Like keeping up with the state of the art research and working on that, being a part of that. So being part of this journey of finding new things, new answers in physics and about reality.
That sounds like a very, very achievable goal for you, and I really hope it works out. Islam Khan, thank you so much for joining me on the program. Your enthusiasm has been just infectious. I feel more educated and more excited about the greater picture when it comes to space and the universe. So thank you for that. I really appreciate it.
Yeah, certainly. It's a pleasure.